All right, guys, welcome back to our last talk before the lunch break. This one's going to be short but good. There's a lot that we're packing in here. So first off, I am very excited to introduce Kent McLeod, who is joining us from a place that I neglected to ask him about. Where are you, Kent? Can you hear me?
I am. Can you hear me?
Yes.
Yeah, I am streaming from Sydney, Australia, so 18 hours in the future.
Oh my gosh, Kent from the future. I love that. Kent is an operating systems engineer at Cry10. He specializes in formally verifiable, trustworthy systems using Cell4. So he is all about putting the beam on bare metal in a way where it can connect to the highly untrustworthy internet and still be secure. He is also joined today by his colleague, Ihor. And Ihor is a professor at University of New South Wales. He is also an engineer at Cry10. And I'm just going to hand it over to you guys without further ado. Take it away, Kent.
Okay. Thanks very much. So yes, I'm Kent. Unfortunately, I had planned to attend physically, but wasn't able to make it in the end. So Ihor is going to be my corporeal form, and I'm going to be over here in the internet. And today I'm going to be talking about freestanding Erlang, so how we are porting Beam to run unmodified in embedded freestanding environments. And I've got to figure out how to drive my slides. Okay, so basically, we're talking about connected industrial devices. So this is software that is actually out there participating in the real world. So it's connected, it's sending data from factories or from like on a power pole somewhere. It's high value, so the task is worth much more than the device, and downtime is expensive and or dangerous. So it's different from software that's running on a server in a cloud somewhere. It's actually out there in the real world where it's running in rugged environments. It's potentially experiencing a lot more unexpected faults or error conditions that you might not get in a virtual environment. And because of that, security and resilience is a lot more important. It's not enough that the software does what it's supposed to do. It also has to, it's not allowed to do what it's not supposed to do. And this is because the level of harm or the level of damage that a failure or a fault could have can be a lot greater than if the software is just running in a virtual application somewhere on a local machine. I think, as Amos said in the panel yesterday, every device is potentially becoming a botnet, and it's really important to make sure that you're writing your software so that it is controlled and it's not causing more harm than the value that you're creating. So most software today runs on these general purpose operating systems. We have applications up the top sitting on a huge amount of shared trusted computing-based operating system code. So in a world where we're running Beam applications, you have a Beam running on this in app 1 and maybe have some other application running on app 2, and then you have all of this underlying system code. And so when you're trying to ensure that your system is not doing anything that it's not supposed to be doing, you're thinking about it in terms of, is it getting into any invalid states, or is it doing any behaviors that are not allowed? And when you're looking at the system as a whole, there is a lot of state that's underneath the application running in the trusted computing base. And if you're wanting to ensure that it's behaving properly, you sort of have to rely on all of the software. And every time you're deploying, running an update, pulling an update of, say, an operating system like Linux, you're trusting that all of the code running in the privileged mode in the processor is correct. And realistically, we aren't able to write software correct at that scale. So at Cry10, we're sort of trying to take a different approach where instead of having a monolithic system, we have a much flatter privileged execution runtime, which is a microkernel. And then applications and the rest of the system functionality is scaled out more horizontally in applications at user level. And what this means is that we're allowed to take big fat applications like the Beam runtime and all of the application that runs on top and isolate it from the system services like the Ethernet driver or a digital bus driver, and ensure that the underlying privileged runtime is only responsible for enforcing the isolation between the components, providing low access to system resources, and allowing primitive communication mechanisms like IPC, like signaling and shared memory. And what that allows you to do is you can implement these system level safety properties, such as in this example here, you want to be able to have some digital bus driver like a CAN bus or an I2C bus that's being controlled by some system controller, but you want to be able to monitor it remotely. And so you want to be able to find out information about maybe what statistics it's reading off some sensor, or polling values of some motor controller, and you want to be able to stream that remotely to someone managing it far away. But connecting it to the internet is dangerous, and you don't want necessarily someone from the internet to be able to go and command and control that device in an unauthorized way. And so you can, if you implement a policy, which is say a one-way filter in the middle here, then information is allowed to flow from the digital bus driver and the system controller out to the rest of the system, but it's not allowed to flow into the system from the outside world. And that can be implemented using a simple shared memory channel between two components, with one channel, one direction is read only and the other channel is read write. And what that means is that in order to convince yourself that the system implements that safety property correctly, you need to trust this bottom level privileged runtime, which is minimal, and you can actually verify that it's correct. You need to trust the implementation of the component implementing the filter, and you need to trust that you've defined the system policies correctly. And so you don't necessarily need to trust everything inside the Beam component, because the parts that's implementing the safety property, you can factor it out of the Beam component and put it in the tiny little program that you write in C, or you get someone else to write it. Maybe they write it in Rust, and you can just focus on verifying or assuring that that 100 lines of code is correct. And so then basically these minimal application environments that each of these user level components are running in, so up the top here, like unlike a conventional system environment on top of Linux, you actually have a very, very minimal set of hardware mechanisms and features that you're able to run on. So in our system here, you have some 32-bit low power ARM CPU, there's a single thread, and your application starts with a number of binaries loaded into its virtual address space. And from there, it has a very small number of primitive operations in addition to all of the user level ARM ISA instructions that it can run. You have these primitive operations for creating threads. Threads need to communicate with each other, so you can have these notifications where you can create notifications. Signal allows you to signal a notification. Await allows you to block and receive messages on a notification. Poll allows you to non-block receive messages on a notification. You have these timeout operations for programming, opening a timeout channel for a thread, programming a timeout to come in the future, canceling a timeout, getting a timestamp, and potentially, if you want to have a fault, you can generate a restart, which resets your environment. And then some message handling functionality for doing more controlled cross-application communication between different applications. So some message calls. We're not really going to be talking about that much today, because most of the implementation is going to be implemented inside the single application environment. And for debugging and development, you have some printf. So basically, how are we going to get from a system like this, where you have Beam, a lot of functionality, a lot of dependence on underlying operating system, to a system like this, where basically have no OS functionality underneath, a few system services running it, separate apps at user level, And then most of the local OS system call is actually implemented inside the Beam OS, inside the Beam components. It's kind of like a library OS. And so basically, the key to this is the C library, which is providing the system interface. So in a POSIX world, the C library provides a POSIX standard implementation of a lot of system functionality. So I was looking at the C library that we're using, which is libmuscle, brilliant C library. It has on the ARM platform, on ARM, it has about 1,600 externally visible functions in the text segment. And then of those functions, about 200 pass all the way through. You end up with about 200, greater than 200 system calls. There's actually about 400 defined system calls, but I think a lot of them are duplicates. So I'm starting saying there's about 200. And basically what happens is, so some functions like stir copy, it's just implemented as a function in the C library. Other functions like opening a file, passes through as a system call to the kernel. And then you've got the sort of hybrid function like get time of day, which returns the current time of a particular clock. But traditionally it was passed directly through to the kernel, but due to optimizations and wanting that call to be fast, these days you have these VDSO shared objects that the kernel loads into the address space of every system and provides local fast implementations of system calls. And so when traditionally you'd be doing get time of day, expecting it to be a system call, now it's actually just a local function call. And what that means is we can sort of take that mechanism and take it to the extreme and say, okay, well, what if we just remove the system call mechanism and implement every system call that we can as these VDSO fast system calls, and then still have a little bit of calling out to remote services for things that we can't implement locally. So say maybe getting access to a secure random number generator, sending Ethernet packets, communicating with other processes. And so it's basically the approach that we took. And then implementing a system call ends up being quite simple. So hopefully this text is large enough for everyone seeing, but basically your system call becomes this vsyscall operation, which gives a system call number, looks up a system call in a table that's implemented in the address space. If it finds a system call, it calls it. If it doesn't find the system call, it returns enosys, error not implemented. And we provide a linking argument that allows the C library to load the system call table when it starts up, and every system call operation now just can pass through the system call table and be implemented locally. So what that means, I picked a basic example. Here's an ioctl. As you can see, or maybe you can't see, ioctl is a IO control. So it's an operation that happens on a file descriptor, and it's a way of performing IO control operations on a file descriptor that's able to cut through the abstraction layers and operate on like an underlying file descriptor, if it's a TTY device or if it's a console device or a block device. In this case, our implementation is only telling a system that there's no TTY because we don't implement that. And so this system call ends up being very simple. As you can see, one of the choices we made was to not provide full POSIX compatibility, and that's driven mainly by that's mainly driven by realistically it's not achievable for us to implement a proper POSIX full system implementation for a freestanding embedded environment, and also because we know that the Beam is the only client of our interface. We can sort of specialize and customize our implementation for what the Beam expects, which makes it easier to test, makes it easier to iterate, and it also makes it easier to actually get something finished. So when I was thinking about how to structure this talk, I thought it'd be quite boring to sort of just go through all of the system calls that we implemented, because I wouldn't find that interesting. So instead, I'm sort of just going to walk through what happens when you load the Beam SMP program from scratch and sort of what system calls you roughly need at each point. So when the program starts, control is first passed to LDSO, which is a dynamic linker. The dynamic linker runs. It's responsible for dynamically linking the program and the VDSO. It sets up TLS images, so for thread local storage, it sets up the initial thread pointer. And at this stage, the only two system calls it really needs are set thread area, which sets thread local storage, and set TID address, which actually also has a side effect of returning the thread ID or the process ID. And so implementing these two system calls, we just require a way to set the local storage thread pointer for a thread and for returning a thread number. And then we step on to the next part of the system. So once the dynamic linker runs, eventually control is passed to main in Erl main.c, and then Erl init basically starts running. And the first big function that we care about is erts alloc init, which initializes the Erlang allocators. And so this is where we start thinking about how to do memory management. So for memory management, basically you have two main calls, mmap, munmap. And mmap is responsible for asking the system for more memory. And it's a very complex system call. In our case, we basically implement a narrow subset, which does anonymous memory management and file mapping. And we basically are managing memory that is statically allocated. So when our system starts up, we declare a heap size. And so a contiguous region of memory in virtual memory, we declare as the heap, and that has a particular size that we configure it statically. And then mmap allocates memory out of that. And Erlang or Beam implements its allocators on top of the memory that it allocates from mmap. So because Beam is generally designed for running in large scale machines, it also assumes that a lot of the memory management is being implemented by like an underlying operating system with demand paging and overcommit. And there's a lot of complexity around ensuring that the memory, like that you're allocating memory that you want to use and you can touch it when you want to use it. But in our case, we're basically, all of the memory is allocated, it's made available, and the operating system isn't going to take memory away from the system during runtime, which simplifies the implementation at the expense of potentially overcommitting the amount of system resources to each application, which is more than what they need. So now coming back, so basically Erl init continues running, and the next interesting call is start schedulers. And what this does is it starts up, the system schedulers, the dirty.io schedulers, the aux thread, all of these Erlang schedulers for running Beam processes, Beam bytecode. And it's now where we actually start having to implement more complicated parts of the system. So sysclone provides a functionality for creating threads. And so we have to hook that up to our underlying thread create primitive operation. And then we also have to manage some data structures around keeping track of all of the threads, assigning IDs to threads, implementing sysexit, where a thread exits, it has to be able to synchronously update some variable somewhere in the system for the fact that it's exited. And basically, most of the threading library is implemented in our C library, which is providing a pthread implementation. So ignoring a few simple system calls like get thread ID, get process ID, and all of the signal calls, like all of the signal handling calls, we just have to implement clone, exit, and futex, and that's mostly enough to be able to provide most of the pthread and all of the pthread related functionality. And so, yeah, so clone creates new threads, exit destroys threads. Futex is a fast user level mutex, which essentially provides a mechanism for doing an atomic compare and sleep. So, like a lot of atomic operations and compare and swap. Compare and sleep means that you want to atomically confirm that a variable is a certain value, and if it's not that value, block and go to sleep until it becomes that value. And so we can implement that locally using the underlying notification objects and the ability to block on notifications and signal notifications. So in addition to those three system calls, we also have these sort of event handling system calls. So for pipes, so Erlang uses pipes to send short messages between different schedulers. TimerFD is a way that you can do high precision timeouts on polls, and ePoll is how you can merge a whole lot of different event streams into a single pollable object that gives you one event at a time for scalable blocking on system events. So basically, we're now at the point where we're getting into Erlang code. So Erl init happens, init boot gets called. Eventually, we start executing the start script, start.boot, and we start seeing a lot of these calls to primload, which is where we're now actually starting to load Erlang operations. And that's now we start needing to see, open, read, stat, access, close, all of these system calls relating to virtual file systems. So we need a VFS layer, and we also need a file system to actually hold this beam code that we're loading. So what do we do here? Well, we basically have a file descriptor table, which is just an array holding the number of file descriptors that we want to have. And for our file system, we're using a CPIO archive, which is a read-only in-memory archive that can contain all of these different files. And then when our application starts up and we start up our runtime, we actually just create a hash table of all of the paths to the reference in the CPIO entry. And every time an open happens, we look up the path, we hash the path, we look it up, we find the file reference, and then we can implement our file VFS calls for read, stat, access, close, fcntl, and getting directory stuff. And that's actually pretty much enough to be able to get Beam loading and running in the system. And then at some point, maybe we're doing distribution. So start dist happens, and then you start wanting to have a networking stack. And so networking stack requires implementing a lot of the socket system calls and providing a networking stack underneath LWIP. And yeah, so then once we get to the end, what can we do? We have, we can run scenic applications. We can remotely render them over the network. We can serve Phoenix Live Dashboard over WebSockets. We can connect to a remote IEX, connect an IEX shell remotely to a component and monitor it remotely. And looking at my time, I'm gonna quickly skim through the rest. So basically, some of the principles that we followed was prefer local and private system state over shared state. What that means is that essentially each process gets its own namespace if this was in Linux, but we don't have Linux. What that means is that state is private by default, so you don't have to worry about interference from other applications corrupting your state, which makes it easier to write code that has to be less suspicious. Avoid system management APIs, so things that change the system, like fork, exec, set time of day, we don't have them. They provide a lot of non-determinism in the behavior that the system can get. As I mentioned earlier, over-specializing in exchange for reductions in complexity. So a lot of these system calls like poll, select, futex are really complicated in a system like Linux because they have to work across multiple applications. They have to work across forking and spawning, and we don't have any of that. So it simplifies the implementation. Then, yeah, so let it crash. Sometimes when we run up against functionality that we haven't implemented, we trigger a crash rather than try to handle it. Implementing minimal functionality by default, but we allow extensions with modules. So things like an LWIP networking stack or a network file system, they can be added in as additional applications that install themselves as system calls, and then the system can run with that functionality when you want it, but not run when you don't want it. And finally, removing sources of non-determinism. And the biggest example here is not implementing POSIX signals, because that effectively means that if you're having signal handling at any point in your code, your thread can be preempted and run somewhere else. And that makes it really hard to know what your code is doing. And Beam doesn't really use POSIX signals if you're not using spawn or create. And so it can actually drop a lot of complexity by just not implementing it. How do we actually validate that we've done this correctly? So using a lot of asserts for invariance, writing our own tests, but also using a lot of libc specification tests for C implementations, and then running the Erlang, the Beam common test framework tests. So like running, say, like all of the stdlib tests. It's kind of a pain to go through some of them and factor out some of the tests that we don't implement underlying functionality for. So anything that spawns a remote node, we can't really handle at the moment, and we don't know if we're going to be able to handle it, or as in if we intend to handle it. Yeah, I was going to talk about some weird bugs that I found. Probably most interesting one, most annoying one was that system calls encode 64-bit variables pretty much arbitrarily on system calls. pread and preadv swap them. Sometimes it's a high-low, sometimes it's low-high. Leads to files being 64 terabytes when you get the offsets wrong. Yeah, basically, we're just going to skip ahead to the end. That's a list of all of the system calls that we implemented. Thanks for coming to my talk. Sorry that I finished a bit over time. It's very bizarre, sort of talking without any feedback from the audience.
All right, thank you so much, Kent. Let's hear it.